So I hope everyone understood this relation. So variation of acceleration due to gravity to the depth and altitude. So with depth it increases linearly with distance increases and distance measured from the center of the earth. On the surface maximum. As we go above the surface means height increases. Again it start decreasing. And it exponentially decay. We are not touching it to the zero line because we don't know at what point the acceleration due to gravity is zero. The third point of discussion is variation of acceleration due to gravity with latitude. So in that we can consider two cases. So case number one by considering rotation of earth and case number two is by considering shape of earth. By considering both the cases we get the same conclusion. But here we first obtain by considering rotation of earth. You know that earth is rotated about its own axis which is passing through the pole. Now we consider the rotation of earth. Now we consider earth is rotated about an axis passing through its pole or polar axis. Now I am considering a particle whose mass is m placed at point P as shown in figure. So this is the point P, and at that point P the particle whose mass m is placed. Now we consider here. So this is a pole. So this is pole and this is the equator. So this is the equator. Now here the particle is at point P. When Earth rotates about the polar axis, this particle also rotates. Now let r, small r be the radius of this circular path of this particle. Now on this particle, centripetal force is acting. And that centripetal force or centrifugal force we write, and it is equal to, it is also called as radial force. As well as we can say that on this particle, a radial acceleration is acting, radial acceleration is there or centripetal acceleration is there. And that acceleration is given by formula r omega square. Now here, the particle P is placed at particle is placed at point P. The latitude for that particle is theta. Now what is latitude? Latitude means angle with equator, that you remember. So this is point P. Then angle with equator is theta. Now this angle is also theta. Then this radial acceleration or centripetal acceleration resolve into two components. So here this is the adjacent component. So it is AR cos theta. And one more component we can show to this side, it is AR sin theta. Okay. So we resolve this acceleration into two components. Now I consider theta is the latitude. Latitude means angle with equator. Omega is angular velocity of rotation of Earth. Now see the triangle OPO. OPO dash. In that triangle, cos theta is how much? Cos theta is adjacent side by hypotenuse. You can see here adjacent side is O dash P means small r and hypotenuse is capital R. So we get cos theta is r by r. So by using that we can write small r is equal to r cos theta. Hence centripetal acceleration is, so just we are written formula of centripetal acceleration and it is r omega square. Centripetal acceleration is r omega square. Now let me substitute this r in this formula. Then we get centripetal acceleration is equal to r omega square cos theta. We substitute small r is equal to r cos theta. Then we get acceleration is r omega square cos theta. Now this acceleration, you can see the direction of the acceleration here. This direction of the acceleration you can see, r omega square. Now here we are considering a radial component of this acceleration, or the component of this acceleration along this PO, and it is AR cos theta. You can see the component here, AR cos theta. Now that component we are considering. So I write AR is equal to AR cos theta, or A cos theta. Now we substitute this A in this formula. So we get r omega square into cos theta multiplied by cos theta. So it gives us r omega square cos square theta. So this is a radial component of the centripetal acceleration. And this radial component we can write by AR. So it is acting in this direction. Similarly, the acceleration due to gravity, we can say that, which is acting towards the center. So this acceleration due to gravity is acting towards center. So total acceleration is what? G minus this AR. So total acceleration we can write G, and this acceleration G dash is equal to G minus AR. Okay. AR is this. So we get a formula G minus R omega square cos square theta. Or we can write force. So resultant force. So let me multiply this equation by M. So mg dash is equal to mg into m into this radial acceleration. So mg dash is equal to mg minus m, and this AR is how much? This is r omega square cos square theta that we substitute. Okay, after substitution we get this formula. Then we can take m common and we cancel m from all the side and we get again g dash. So g dash is equal to g minus r omega square cos square theta. So in special cases, case 1, at equator theta is 0. So we get acceleration due to gravity at equator is g minus r omega square. And at pole theta is 90. So we get acceleration due to gravity is equal to g. Now we are discussing variation of acceleration due to gravity due to shape of Earth. The shape of Earth is not a perfect sphere. It is bulge at equator and flat at pole. The formula we learn for the acceleration due to gravity is gm upon r square. In that formula, capital G is the gravitational constant, capital M is the mass of Earth. So capital G and capital M are constant. They are constant. It means that G inversely depends on r square. Larger the radius, smaller the G. G and R relation is inverse. Now you know that if Earth is not a perfect sphere, it is bulge at equator and flat at pole. Means this equatorial radius and polar radius when we compare. So equatorial radius is greater than the polar. So here we can write formula for this G at equator and G at pole. As here radius at equator greater than radius at pole. Hence we can write G at pole greater than G at equator. Radius at equator is greater, therefore acceleration due to gravity at equator is less. Radius at equator is greater, so acceleration due to gravity at equator is less. I hope everyone understood. Same conclusion we get, which we learn by considering the rotation of Earth. The same we get here. So every system always configure itself in order to have minimum potential energy, or every system try to minimize its potential energy. Simple example is So this is a surface. So this is the object. When we lift the object at height h, then potential energy of that object is mgh. Potential energy increases. But as we release this object, then what happens? This object come to the surface again. Means every system always configure itself in order to have minimum potential energy. Means this object is coming down. As it come down, potential energy decreases. It means that it decreases potential energy. Another example. This is spring. The potential energy of the spring is given by formula half kx square. This formula you have to learn later. So this x, as I stretch the spring, means we elongate the spring, potential energy increases because potential energy depends on x. So here the formula is half kx square. So potential energy increase. As we release this, what happen? So this object is pulled towards again its original position. Means again the system try to minimize the potential energy. Always every system try to configure itself to have a minimum potential energy. In general, we can write work done against conservative force acting on object is equal to increase in potential energy of the system. For example, so when we are lifting any object to a certain height, so potential energy increases. So work done by the conservative force is equal to increase in potential energy. So that work done is equal to the potential energy. So we can write here work done is force into displacement. So we can write work done is equal to F into dx is equal to potential energy we write, increase in potential energy we write by du. So we get this formula here. Work done by the force, conservative force is equal to increase in potential energy.